So now we're going to look at how the closed loop bandwidth of circuits, operational amplifier, as we discussed in the last topic, how does that affect the rise time of pulse signal or step signals. So many time our signal, especially if you're using the digital signals, many time our signals are pulse like signals. The values are going from 1 to 0, and the idea is, since you looked in the first chapter, the internal circuitry of operational amplifier, there were a bunch of capacitor, bunch of transistors, and each transistor has capacitors between the base, emitter, base, collector, and stuff, collector and emitter. So anytime you have capacitive circuits, anytime you have inductive circuit, whether they are outside the circuit or inside the IC, these capacitor takes some time to charge, to produce level 1, and discharge to produce level 0. So anytime you apply a pulse, rise time due to the closed loop bandwidth is defined as the time during which the pulse level goes from 10% of its value to 90% of its value. So look at the gain. They're showing you gain over here, right? So basically what they are showing is, if your input signal is going from 0 to 1, so let's say it was 0 before time t is equal to 0, and then it goes to 1. So it is like a step signal. The output is not instantaneous gonna go from 0 to 1. The gain over here, they're showing gain, but in general we're talking about output because output depends on the gain. So the closed loop gain, in this case, they are showing that it's not going from 0 to 1 instantaneously, rather it is taking an exponential approach. Why exponential approach? Again, we discussed in circuit analysis that your RC circuit, when they are charging, then based on the time constant of the RC circuit, it is going to charge exponentially before it will hit its steady state value. So the same concept over here. The internal capacitors are charging to hold the maximum value at the output, and because they are charging, they are going to take an exponential trajectory, an exponential path, to go from 0 to the peak value. And this is the output they're showing. Sorry, I said this is the gain that's shown. They're the output that's showing, because they're multiplying the gain times the input. So due to the closed loop bandwidth, the rise time is defined as the time that it is going to take for the output waveform to go from 10% of its value to 90% of its value. So in pretty soon we're gonna look at another rise time due to the slew rate. So they are two different rise times that we're gonna look at. But due to the closed loop bandwidth, it is from 10% to 90% of the output value. And this time is defined as the time due to the closed loop bandwidth, or TCL. And in general, for the first order circuit, it is 0.35, a number that they have derived. We are not showing the derivation. 0.35 over the closed loop bandwidth. So as you can see, this is inversely proportional to the closed loop bandwidth. TCL is inversely proportional to the closed loop bandwidth. That is, when your closed loop bandwidth is smaller, the rise time is going to be larger. And when your closed loop bandwidth is larger, the rise time is going to be smaller. Now, what is slew rate? So one is the rise time due to the closed loop bandwidth, how it's going to affect the output going from 0 to 1, or 0 to the peak value, not 1 but peak value. What is slew rate? And these two things, slew rate and closed loop bandwidth, you have to consider them to know the proper frequency at which you can operate the circuit, or the proper rise time of the input for which the output can follow the input. Because remember, for an amplifier, output must follow the inputs. That is, the shape of the output must be the same as shape of the input. If it is not, then we don't consider it as a linear amplifier. It is not doing linear amplification. So closed loop bandwidth is one factor that affect the output. The other factor is slew rate. And how does slew rate affect the output? Once again, depends on the capacitor. Within the circuitry, you have capacitor to stabilize the closed loop operation of the circuit. And again, as we discussed, the capacitor needs to be charged and discharged as your input signal is varying, whether that input signal is a digital signal, ones and zeros, or a sinusoidal signal, but they will be charging and discharging, right? Now, when they charge and discharge, then they pose a limit as how fast the input signal should change, such that this charging and discharging happens in such a fashion that the output signal can follow the input signal. So the shape will not change. Remember, once again, charging and discharging of these capacitors, whether they are inside the circuit or outside the circuit, they need to consider that time, the charging and discharging time, such that the output should follow the input. So in other words, if the input frequency increases so fast that the charging and discharging of the capacitor is taking longer than the cycles of the input, then the output cannot follow that fast cycle, because again the output depends upon how fast the capacitor is charging and discharging. And if that time becomes larger than the time it is taking for one cycle of the input, then the output shape and the input shape will be different. So that's why this study is important, as what are the limitations, what frequency should we use at the input, what rise time should we use if it's a pulse signal. That's a study that we are doing right now. So this is slew rate. Again, it employs a limitation which is called slew rate limitation, and that limitation again is, hey, what frequency you can use maximum frequency at the input so that your output will be linearly dependent on the input frequency, or your output if it's a pulse signal, or the shape of the output pulse signal, that is the rise time and everything, can faithfully follow the input rise time. So slew rate is represented by volt per second. That is how fast the voltage at the output can change in 1 second. That is represented by the slew rate, and generally it is represented, a second is a big unit, so it's represented as volt per microsecond. So for 741, the value of slew rate is 0.5 volt per microsecond. So the output of of your 741 can change 0.5 volt in each microsecond. And again, that poses a limit on how fast the operation can be done with 741. Now there are other operational amplifier that actually slew rate is lower than 0.5 volt per microsecond, so they can work with even faster application than 741. So earlier we looked at the rise time due to the closed loop bandwidth, and here the rise time due to the slew rate, TSR. TSR is the rise time of the wave of the pulse due to the slew rate, which is of course volt per second. So your output voltage from 0 to the maximum, or if I show the rise time, so 0 to the maximum, this is the rise time. So it's not from 10% to 90%, as we looked at in the case of closed loop bandwidth. In this case, it is 0 to maximum. So there is a difference between the two, due to the closed loop bandwidth and due to the slew rate. And we notice the peak value, S is the slew rate. So when you use this is the unit over here is volt, the unit over here is volt per microsecond. So your answer is going to be in microsecond for slew rate, rise time due to slew rate. So this is the equation that we're going to use if our input signal is a pulse type signal. And this is what I'm explaining. Okay, so here is an example. Here in A, this is your input pulse signal. This is the rise time of the input pulse signal, Ti. And if this rise time is larger than TSR, then the output will faithfully follow the input, and the output is going to be the closed loop gain times the V input. But if your input rise time is less than TSR, then the output TSR, I'm showing the slew rate time of your 741, that is in this case 0.5 volt per microsecond. That's what I'm referring to. So your output is going to take longer to change. It is not going to be a faithful replica of the input, so there will be a delay in the output, and that delay is basically, it requires that time to go from 0 to 1 TSR, which is 0.5 volt per microsecond for 741, and other operational amplifiers have different. So in this case, basically your output is not faithfully following the input. It is not linearly following the input. So that's the effect of the TSR, the time, rise time due to slew rate. Okay, now if your input signal is sinusoidal like signal, that is a signal with complex frequency, then how the slew rate is going to affect, that is how you will set the frequency of the input waveform such that the output can follow the input, that is they have the same frequency. Phase can be different of course, but they have the same frequency. So we do a little derivation. We assume that the output is V out sine omega t or cosine omega t, whatever you want to call it, and then the rate of change of the output. Remember, slew rate is V naught over T, TSR or whatever we call it, right? So rate of change of the input, we take the derivative of this, omega V naught cosine omega t, and then we look at the maximum rate of change, that is when cosine becomes 1, which is omega V naught. So the slew rate has to be greater or equal to the maximum rate of change in order for the output to follow the input. So slew rate has to be greater or equal to omega V naught in order for the output to follow the input. So if you have an input signal and so if you have FSR, highest frequency at which the output signal can track the input signal due to slew rate limitation. So we are looking over here as what can be the highest frequency at which your output signal can follow the input signal. We are saying that that's FSR. We are defining that frequency at FSR. That can be 20 kilohertz, 30 kilohertz, and if it is more than that, then the output signal will not follow the input signal. That is if input frequency, as long as it is below FSR, output will follow that. If it is more than FSR, output will not follow that. So since slew rate has to be greater or equal to omega V naught and omega is 2 pi f, f is less or equal to s divided by 2 pi V naught. So the highest frequency at which the output is going to follow the input, we are calling it FSR, and that will be the equality sign. Of course it can go below that, but the maximum value is going to be when this is equality. So FSR is equal to s over 2 pi V naught. And that's the limitation of the frequency of the input on the slew rate. So let's look at a few examples. This is for the digital. So you have a digital signal, level 1 and 0 pulse, and this is your 6 volt, this is your 0 volt. And we are asking what was the minimum rise time such that the output signal will be undistorted due to slew rate restriction. So we use the equation, slew rate has to be greater or equal to V naught over the rise time due to the slew rate, and from that we can calculate the rise time due to the slew rate for 741. We know S is 0.5 volt per microsecond, so the rise time due to the slew rate comes out to be 12 microseconds. So minimum rise time of the input waveform must be 12 microsecond. Maximum can be more than 12 microsecond, that's fine, but minimum can be 12 microsecond. It cannot go below 12 microsecond if the output has to follow the input. Another example in which the input is a sinusoidal signal instead of a pulse with the same value, 6 volt and negative 6 volt. And here we are asking what is the maximum frequency of the input signal such that the output can follow that. So FSR equals S over 2 pi V naught. V naught is 6 volt. So we plug in those values and it turns out that output can follow the input maximally at 13.263 kilohertz. So if your input is 14 kilohertz, then the frequency of the input, frequency of the output will be different than frequency of the input. It will not be able to follow the input. Okay, now let's go ahead and discuss this in the same topic because it relates to linear bandwidth and slew rate. So for any application where you're using frequency or a pulse signal, that is the rise time, you have to consider the restriction because of both the closed loop bandwidth and slew rate. And if it's a pulse signal, then your input rise time should agree with both the input rise time due to the closed loop bandwidth, that is TCL is equal to 0.35 over Kn, and 0.35 over BCL, and it should agree with, it should satisfy the rise time due to slew rate, that is TSR is equal to V naught over S. So if you have the input signal as a digital pulse or a step signal, then the rise time should satisfy the condition for both closed loop bandwidth restriction and slew rate restriction in order for the output to linearly follow the input. Likewise, if your input signal is a sinusoidal signal, then the frequency of the input sinusoid again should satisfy both the limitation by the closed loop bandwidth and by the slew rate in order for your output to faithfully follow the input. So if the highest frequency in the input is FH, so if you have a complex signal with many frequencies or harmonics, if the highest value of the harmonic or highest frequency is FH in the input signal, then FH has to be quite smaller than BCL and FH has to be smaller than FSR. So one is quite smaller and one is only smaller. Why? Because remember at BCL, the gain of the amplifier is already down to 70.7% of the peak gain, right? 1 over square root of 2. So that means if it is closer to the operating frequency is closer to BCL, then your gain would already be down. You know, it's not going to be close to A naught. So that's why we want the operating frequency to be quite smaller than BCL. So let's say in this range somewhere where the gain is not that much down from the actual value of the ACL. And FH is just less than FSR, as we discussed just on the last slide, that FSR is the frequency at which the output can faithfully follow the input. So your input frequency just need to be smaller than FSR in order for the output to follow the input. It doesn't have to be quite smaller. But in any case, we have to satisfy both conditions in order for the output to follow the input frequency faithfully linearly if our input is a sinusoidal signal. If our input is a step signal, then we have to follow the restriction imposed by both closed loop bandwidth and the slew rate in order to have the rise time of the input such that the output can follow the input signal. That is, the output rise time will match the input rise time. So what are the conditions? Again, the input rise time Ti has to be quite larger than the rise time due to closed loop bandwidth. Why it is quite larger? Again, because rise time due to closed loop bandwidth is smaller. Remember, it's from 10% to 90%. Whereas the rise time due to the slew rate is the complete from 0 to the peak value, 0 to 100%. So rise time due to the closed loop bandwidth, we use quite larger inequality, and rise time due to the slew rate, we use just larger inequality. So these two conditions must be satisfied in order for the output, if it's a pulse signal, for the output to follow the input faithfully and linearly. So there are some examples. Alright, in this example, again my amplifier is the inverting amplifier, and RI is 4 kilo ohm, RF is 40 kilo ohm, and input is 20 cosine omega t. So it is asking you what must be the input. Observe that I did not choose any value of omega or f here. Question is, what should be the maximum value of omega or f in order for the output to linearly follow the input? So first, so I have to check both conditions. I have to check the condition FH should be quite smaller than BCL and FH to be smaller than FSR. So you can go over this, and then at the end you will see that, let's see, BCL came out to be 90.90 kilohertz. That's the value of BCL that came out to be. And then FSR came out to be 397.8 kilohertz. So in order to satisfy both these values, the input frequency has to be smaller than the smaller of the two values. So the input frequency has to be, the highest input frequency has to be smaller than 90.90 kilohertz. And since this is BCL, it has to be quite smaller than 90.9 kilohertz. So the input highest frequency has to be quite smaller than 90.9 kilohertz in order for the output to linearly follow the input. Okay, the same problem, but we change the input value to 100 millivolt. Again, we found out BCL is going to be the same because BCL equation is B over Kn. It does not depend on the output voltage. It only depends on the values of B and values of the resistors. So BCL will still be same, 90.9 kilohertz. But FSR, since it depends on the output voltage, it will change. And the new value of the frequency, highest frequency due to the slew rate, comes out to be 79.57 kilohertz. So now in this case, FSR becomes smaller than BCL. So now if we choose a frequency which is lower than FSR for the input highest frequency, then it will satisfy both conditions, and that will be the case for the highest frequency at which the output will be able to follow the input. Another example in which the input is not a sinusoidal signal, but it is a pulse signal as it is shown here, and peak value of the input is 20 millivolt. So now you have to define, you have to determine what will be the lowest value of your input rise time such that the output can follow the input. So two conditions again, Ti has to be quite smaller than TCL, and Ti has to be smaller than TSR. So first we calculate TCL, 0.35 over BCL, and it came out to be 14.35 microsecond. And then we calculate TSR, which is V0 over S. V0 of course is ACL ideal times Vn. We are just using ACL ideal because again the actual value and the ideal value are pretty closer to each other. ACL ideal time Vn. So we calculated and it came out to be 1.64 microsecond. So Ti has to be quite larger than TCL, and Ti has to be larger than TSR. So in this case, the highest of the two is going to satisfy the condition, and in this case highest of the two is 14.35 microsecond. So Ti has to be larger than 14.35 microsecond in order to satisfy both condition and in order for the output rise time to be equal to the input rise time. So for time, remember time, it is, you're comparing the greater condition, because if it's smaller than a specific value, the output cannot follow the input. If it is greater than a specific value, then yes, output can still follow the input. For the frequency, you're using less. The highest frequency should be less than FSR and quite smaller than PCM. And in the next video, we're going to discuss noise in operational amplifier.